Okay. So I'm not expecting anyone to have started milestone 2 by this time. So this tutorial will get you started with milestone 2, but we really recommend you start as early as possible because there will be a lot of stuff to do. So do start during reading week. Let's go. Initial steps. First thing, download the MQ handout. There is a walkthrough section in section 4, and that will tell you how to set up your project. Read the EasyGL Quick Start Guide. So EasyGL is the package that we are using for graphics. Modify main.cpp to let your main program starting to draw the graphics and begin implementing the actual draw map function. How do you modify your main function? First, remember to include the m2.h header file in your main.cpp. And you should be looking into it. It should be at the same place as m1.h. So look into it to see your expectations. And in the main function, you only need to add one line, which is the call to draw map. Make sure you call draw map in between your load map and your close map. So this is making sure that you have loaded map before drawing and you are not erasing your map before drawing. You're closing the map after drawing, after draw map returns. First step, we're doing this step by step so that we are not missing anything and we can make sure that we fix all of the bugs before proceeding. So the first step is to create an empty window like this. So this doesn't have a canvas. It's not drawing anything. You have the program title here. You should be modifying this name to something more interesting, to be the actual name of your map. You have the buttons here. So in your file that contains your draw map, first remember to also include the m2.h header file and also the EasyGL headers. These are the files that you can also find in your header file folder, and please read them in detail because these will be the functions to call when you're drawing, and you'll just need them for drawing all of the things you need to draw for the map. And then this chunk of code is the setup for EasyGL configuration. So first, we have an application settings. And then in the settings, we are defining the main UI resource to be this file. This main.ui will define your initial window layout. And this is in your repo. You can modify this. Settings.window identifier, we're setting it to main window and the canvas to the main canvas. After we have these, we create the actual EasyGL application using the settings. And then we run the application by passing the control to EasyGL. And this application.run, it will open the graphics window and it will return when you close the graphics window. So you will be in the graphics window until you decide to close it and the program will end. You may notice these 4 null pointers. We will talk about them later. Now, because we are just doing an empty window, we are not using anything here. In the empty window, we have the pen buttons, which are the buttons to help you move the canvas, like move the map. The zoom buttons and proceed will close the window and continue. So the demos in this tutorial will just be showing you everything in code and just showing you that it actually works. Draw map minimal is the same function that I just showed you. It pulls these things. So it has everything that I just showed you. And if you look in the source, you have the libstreetmap resources main.ui. You don't need to understand all of these now, but when you are adding things, you can refer to that. And in the source EasyGL folder, you have a lot of header files and CPP files that you can read in case you need to. So if we are just using the minimal draw map, let's see what happens. I'll just compile and run in the terminal. If you want to use code, you can use VS Code. So I compiled and I ran with Mapper. Here is the window that shows up. And it's the same window that's in the slide. And you have all of these buttons. And currently, because we don't have a canvas, when you click on one of these buttons, it will say could not find canvas and Zegful. So the next thing is to actually create a canvas and make sure we can draw on it. To define a canvas, before the run, we want to first do a rectangular canvas initial world to 0, to 100, 1,000, 1,000. 0, is the bottom left corner, 1,000, 1,000 is the top right corner of your entire canvas. And you can add the canvas into the application by add canvas using the same name as here, main canvas. And draw main canvas is the actual function that's used to draw the canvas. And the coordinate system is set to initial world, which is this one. And this draw main canvas, we're referring that as the callback function. So when we are running application.run, this command will call this function, which is why we also need to create this function as well in the same file. So the callback function has a fixed set of parameters passing into it. These are just fixed. You just copy them. And the draw canvas function will have the renderer pointer. And using g.drawRectangle, we'll draw a rectangle onto the canvas. And for now, we're just having a main canvas and we are drawing a rectangle around it. And rectangles often just takes two arguments, the bottom left corner and the top right corner. And here is what it will look like. The bottom left corner at 0, 0, top right corner at 1,000, 1,000. And I'll show that to you in code. comment out the first one and go to the blank canvas one, which is this one. So here are the same things: initial world and add canvas. Then we will have a callback function, draw main canvas blank. And if we search for that, it's here. And in here, we are first setting the color to be 000. That's the RGB value for black. Set line width to 10. So this is the rectangle line width that we want to use, and the draw rectangle of the bottom left and top right. Let's see that running. So save, compile, and run. We'll see this. And you can zoom in and out with mouse scrolls or using the buttons. Both will work. And proceed will close the window. Okay. Next, we want to actually draw something interesting. Let's draw the intersections in Toronto. So as in milestone 1, you also need to load in the data so that you can access them faster. And in this tutorial, we're going to load in them as a vector of struct of intersection data. So for each intersection, we're recording their position in lat long and their name. And in the draw map function, we're going to load in this vector. How would you write the code to initialize this vector, to fill in this vector? Familiar with it from milestone 1? So you first resize the intersections vector to be the non-intersections, and then you loop through all of the intersections and fill in the data. And you may have others that have code, but now we're only interested in intersections. Don't really, just look for what I said. I think these slides are just from previous years. So. Now, in the draw main canvas, we draw each intersection onto the canvas by also using a for loop, looping through all of the intersections, and we get the lat long values, longitude and latitude as xy. We want to just assign the width to be a random number, let's say 10, and the height to be the same as width. So we're drawing squares and call fill rectangle. So draw rectangle will draw a rectangle with line. Fill rectangle will fill in that entire rectangle. So this means we are drawing solid squares. And this also takes in the bottom left and top right. Yeah. So in the initial database, we don't have that, but you can use some more later to get the opacities. For the initial ones, it just takes the RGB and will just fill with solid. So if you want to show something on top of each other, you need to make sure that you're first drawing the bottom one first. And here is what you will see. I see the initial rectangle, and you see all of the intersections here. And why is that? Any thoughts? Remember, the code looks like this. No, the width and height are the same because the drawing squares. But what the positions are in the positions are depending on x and y. So that what values are x and y? Yeah, and what value is that usually for Toronto? Like what are longitude and latitude? Yeah, and we are having a really small like coordinate system. Yeah, because latitude and longitude within a same city is really small. Like it differs by really small amounts. And latitude and longitude are actually angles. Angles on the Earth. And the coordinate system we're using is 0 to 1000. So this will not show anything relative to the last ones. I just need to show you that first, and then we can move on to how we can visualize the actual map. So the code is the same, so I'm just not repeating that. Like here is how you fill the vector, and the draw main canvas XY is here. And it's the same code. Make and draw. This is what we get. And if we zoom in, it's a square. And then this slide is just repeating what I just said, because latitude and longitude are not in the same coordinate system we have. So we want to set our coordinate system to be the actual bound of the map. So we want to find the maximum and minimum latitude and longitude for our map that we're showing. So how would we find out the maximum and minimum latitude and longitude? That's our set of data points. Yes. We go through all of the intersections. So first, we want to initialize these values, the maximum and minimum latitude and longitude in the city. So what is the best thing to initialize those two? Not really. There can be negative ones. Yeah. Let me repeat the things before to you because it's a bit complicated. We are just following the steps. So for M2, the first thing is to modify main by including the m2.h. You have your functions, the functions you need in there, and put in draw map in between the load map and close map. Then you need to write the draw map. So the draw map will start with settings, and these are just the commands to set the settings. Then create an application with the settings. So the main.ui is just the window layout. And hitting applications.run will create this window with an empty canvas, like no canvas. There's nothing. And the program name is here. You are expected to change this name to be the actual map name. And you have the pan buttons, zoom buttons, and close. So proceed will close the window and continue in the program. And then we want to have something in the canvas. So we initialize the canvas to be from 00 to 1000, and add the canvas as main canvas. Draw main canvas is the callback function registered for this canvas. 00 is the bottom left corner, 1000 is top right. Draw main canvas is the callback function we register for drawing canvas. And initial world is this thing. So which means we need to write the draw main canvas to do the actual drawing. And in the draw main canvas, in this case, we're just doing the draw rectangle around the entire canvas. And after that, it looks like this. So we have the bottom left and the top right. Then when we want to draw the intersections, we want to store the intersection data first with position name. So we're just creating a vector to store the intersection data with position name for each one. And we load in that at the beginning of draw map. Then to draw everything, we just loop through everything. And then in this case, we're just having the coordinates to be latitude and longitude. And setting the width and height to 10. Like currently, we're just drawing with latitude and longitude. And then we will get this. All of the intersections are here. And this is because the latitude and longitudes are small angles relative to the entire like initialized world, which is 002,000. So now we want to set the map bounds to be the actual map bounds, which is why we want to find the minimum and maximum latitude and longitude. So how should we, let's go back to our question. How should we initialize the maximum and minimum latitude and longitude? Like what do we write here? It can be negative, so we can't do 0 for minimum, maximum. And it may be for any city in on the earth. What is the best value to initialize them before going into the actual for loop? Like for max and min. But it could not be Toronto or any. We don't want any magic numbers for coding style. Very simple value you can assign to. It's never going to go wrong. That's not the one I'm talking about. It's going to be a really, really simple value. And when I show you, you will like, oh, for max and min. If we don't do this initialization, and if we just initialize the coordinate system to be anything, you will get a really, really small map. That's not relative to the actual latitude and longitude. Yeah, previously we used that and we get a really small map. That's not proportional to our canvas. So we want to now set the canvas world coordinate system to be the actual maximum and minimum latitude and longitude of your map. Like it's a point in our map, right? So we can initialize that to a point in our map. So initialize the max and min to be the first point in our map. Not necessarily. We set it to be the first point in our map, and then we go into every single point and compare. So if we initialize it to be a point in our map, it's not going to exceed the maximum and it's not going to be lower than minimum. It can be either be the maximum or minimum or something in the middle. STD max is the STL maximum function that will return the maximum value between the two parameters. Just looking to the specification, I don't have it memorized, but I think it does. Okay, is this clear? Clear for everyone? I'll continue then. So after this, we will have the maximum and minimum latitude and longitude to initialize the world to be. So we do the minimum long, minimum lat, maximum long, maximum lat. And then we do the add canvas with this new initial world. And we draw and we use the same draw main canvas function. And we will get this. So we're zooming into that dot that we just saw. And why is this entirely black? So remember, the function looks like this. Why do we see a black screen? Yeah. So you were but I see a black screen. What's the 10 is too big. 10 is too big relative to our latitude and longitude. So if you draw a 10 by 10 square, that will likely cover everything in your map. If we're drawing with latitude and longitude. So now we want to modify the drawing size. And if we just play around with it, 0.001 will work about fine. And yeah. 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 And then the question to consider when you're writing your own milestone 2 is, should the width and height, which is set to 0.001 now, should them change based on how much you are zooming in? Let's keep that question in mind, and here is what we will get after changing the size of the square to be 0.001. It's this map correct for Toronto. Let's open up Google Maps and see Toronto and see if there are any differences. I'm trying to get a similar zoom level as that. Compare them side by side. No. This and this. Get a smaller zoom level for this one. And close this. How do I close this? Any problem? This is because Google Maps is hiding some of the details when zoomed out. So the number of points is right. But how about the shape? Yeah, it's a bit stretched out. And that's because we're drawing with latitude and longitude. And Toronto is located more in the north side of the Earth. So it's going to be projected slightly stretched out horizontally. I'm just going to show that it's actually the case by modifying the code. So we are first getting the maximum and minimum latitude and longitude using this, and then we're drawing with this, where width and height are 0.001. Let me save it, compile it, and run. So this is the same thing we get in the slides. And if we also compare this with Google Maps, you will see that it's actually stretched out. Where this one is more, it has a steeper slope. If you look at the edge. So let's go back to the slide. We want to then convert the latitude and longitude to Cartesian x and y to show the correct projection. And this conversion is outlined in your milestone 1 handout. And you should be writing your own conversion functions, helper functions, to and from lat longs. So we want to both write the ones to get x from longitude and also the get longitude from x. And in this case, for the entire map, we need to get the average latitude of the map to do the conversions. This is to align the conversions. And this is the closest approximation we can get for the entire map. And then when we get that, we can then change the previous longitude and latitude coordinates to x and y by calling the helper functions. Then the width can be then modified to be in meters. And in this case, we're just setting it to be 100 meters. And this value should change in your code. And then it's just the same thing, fill rectangle with x and y as the bottom left corner, and x plus width, y plus height to be the upper right. Then, because we are changing the coordinates we are drawing, should we also change something else here? What should we change here? What values are we using that were originally lat long and now we want to change them to x and y? We want to change the coordinate system, right? Previously, we're using lat long because now we are drawing with Cartesian x and y. We want to also change the coordinate system to be x and y instead of lat long. Yeah. It's just as simple as using the helper functions. And after this, we will get this. And this is the map that resembles the actual Google map. You will see that these are aligned more. And here is the comparison of the bad projection and a more realistic projection. Let me also show you the proof. So it's going to be the same code that I just showed you. Lat long, it's the same code, and then we're just using the conversions, x from long, y from lat. And in the draw main canvas lat long, which is this one, we're drawing with x and y and 100 meters for each point. And in the code, I'm also doing a timer for each call of draw main canvas. So now let me compile and run. Now we have the actual map, and let's zoom into it. here are all the intersections. And remember, we're still having the question of whether we should adjust the size of the intersections we're drawing dependent on the zoom level. And I think you should have the answer by now. So your draw main canvas function is called every time you zoom in and out, or every time you move through the map. And you will see it here. So this time will be printed out each time you move your map. Show it. And when you zoom out, zoom in. And this is because every time you move something in the map, your canvas will be refreshed. And each time when your canvas refresh, it will call the draw canvas function again. Let me just close it and we can get a cleaner estimate of the time afterwards. And the reason why I'm talking about time is because this function is speed critical, because it will be called many times. It will be called every time the user tries to move in the map. And you will be drawing more things than just intersections. So if you're calling this every time for each intersection, is this wasteful? Because your conversion functions will most likely look like this with a call to the cosine function. And cosine and sine functions are slow. The STL cosine function is really, really slow. So in Toronto, if you are only drawing intersections and not drawing any features, any streets, street segments, any point of interest, it will call this function over 150 million times. This is called every time you want to convert from lat long. And the cosine function is a really slow function. But we want fast redraws because the function will be called many, many times. Ideally, we want each redraw function to take about 10 to 100 milliseconds. And this includes drawing everything to make your map smooth. How do we reduce computation? Yeah, do the conversion beforehand. Pre-compute and store the actual XY coordinates in your data structure. So now I'm changing the position, lat long position of our intersection into X and Y locations. And we're using this EasyGL point2D structure. This type is defined in EasyGL. It can be taken directly by EasyGL. So you don't need to write any additional code. So using this, we can just do in the field rectangle, we can just pass in this position and the width and height. Then it will do the same thing as before. Having the lower left corner at this position and the upper right corner, width and height relative to that. Okay. After we have that, let's compare the speed. I have that in another repo. But also this one. So I will be timing both. So it has the same minimum and maximum lat length. Then initial world from main canvas faster projection. And in here, we're storing the X and Y locations and also timing them. We're using the X and Y location and we're timing them. So let me go into here, make and let's just time the initial load of the map. I'll run this and post. Here is the time. Calling the conversion function every time. And let me run this one. 0.006 to 0.004. See the difference? And let's go back to the slides. And because these values were obtained at another time with another machine, so they will vary slightly, but usually we will get a 1.5x speed up to display the whole map. And if we zoom in, it will be a 2x speed up, and we will get faster redraws when we are zoomed in because it's just something in EasyGL. It doesn't take that much time to render objects that are off the screen. Everything's clear until this point. After this, let's add an interaction. So now I want to modify our map with intersections so that when we click on one intersection, we will highlight it by drawing it in red. So what we should do now is that when we are calling the application.run, remember previously it was 4 null pointers. Now we are changing the second one to be act on mouse click. That is the callback function we register for mouse click. And all of the callback functions are registered to have the same set of parameters. So for mouse click, we have the application, we have the event being mouse click, and we have double X and Y being the coordinates that being clicked on. And in the default function, we have an output to the terminal saying mouse click at these two coordinates. So now we have the mouse click coordinates. How do we find which intersection we click on? Like the answer is right there. So your program draws all of the intersections in X and Y. And you can detect the mouse click at X and Y. How do you find the closest intersection? You're finding the closest intersection, and you have the find closest intersection function in M1. So you're clicking on the screen, and you have the X and Y coordinates of that click. And it's never going to be exactly the same as any intersection because there's like differences in the human action and the actual values, and there will be uncertainties. So we want to find the closest intersection by calling the find closest intersection function from M1. And because that takes in a lat long value, you want to convert the X and Y into lat longs. So that is a reverse conversion from X and Y. So we find the closest intersection and we can then output the intersection ID. And we can get the intersection data from that intersection ID. Right. Now, if we want to highlight it, it's just simple. We draw a red square at that intersection location. So this is getting the renderer object G from the application that's passed in here. We get the renderer G, and then we use the G to draw. Set color to red. So we have EasyGL constants defined in the library with all of the constants, all of the colors that are common to use. And you can define new ones from RGB values. And we draw the rectangle. We draw the square in red, filled with red. And let me show you what the code does. It's this terminal.
What is the fill rectangle?
Fill rectangle will draw a rectangle that's filled with color. It will draw a solid rectangle. Draw rectangle will draw a rectangle that's outlined with line and nothing in between. So this function is the same function that we just did with the act on mouse click stateless function registered with the application.raw. And if we go to this function, we'll see that we're not using the event, so we're commenting it out, but don't leave this out. We're just leaving the name out because we don't want it to mess up with our code. So we have everything and all of the code are the same. Let me go, did I not save? I didn't save. Okay, compile. And run. Now, Let's zoom in. And we can start highlighting. Okay. Now let's try moving it. Did you notice something that shouldn't happen? No, the box is not off. But when you move, it will disappear. And when you zoom in and out, it will disappear. It's a bit off because there's another one that's just underneath it, which shouldn't happen. And why is that? Yes, because we didn't keep that when we are redrawing. So the next thing is to save that as a state. Save a state of whether we are highlighting this intersection or not. And so we know in our redraw function, we can either draw that in black or draw that in red. So how? First thing, we register our callback function, mouse click event. We write callback function that finds the intersection closest to the click. And now we don't draw it. We record it that it's highlighted so that the redraw function knows it's highlighted. So then we modify the redraw function to highlight the ones that are reported to be highlighted. So in DrawMap, we are still keeping this act on mouse click. And just a general note, if you need to use other things, the general form of these for null pointers is initial setup, act on mouse click, act on mouse move. So this will be the function that's registered when you move a mouse on the screen. Act on key press. This will be the one that's called when you press something on the keyboard. Now we are just using the mouse click one. So then in the act on mouse click, we still find the closest intersection. And we add in another state in the intersection data as highlight. When it's true, we highlight it. When it's false, we draw it as black. And we set the highlight to 2. Now in the redraw function, we then add in a check of whether it's highlighted or not to decide the color we want to draw it in. Clear? If it's clear, I'll go show you the code. So this will be just the same. This is the function where we're setting that dot highlight to 2. And in the redraw, we are drawing with states. States. Okay. Compile. And run. So zoom it in so that we can see better. I'm clicking. Do you see what happened? Nothing happened. But let's move it. I click on this one. That's maybe not obvious. I click on this one. Why is that? Yes, it only updates when you redraw. So when you are first registering it, the redraw function is not called, so nothing will be drawn. Go back and solve this problem. That is a usability problem because even if you highlighted it, it just shows after you move the map somehow. But the users will expect it to appear immediately. So we want to force a redraw by calling app.refreshDrawing. This will force the app to call the redraw function. And this is just a general note. You can display a message at the bottom of the screen using update message and a string. And this string was obtained from a string in this case. So this is just improving usability. You don't have to go back to the terminal to see what's outputted from the program. Is everything on this page clear? Okay. I'll show you the demo. Can't find my mouse. I'll switch to the highlight immediate. It's just the same code I'm showing you. Have the mouse click immediate, which is here. So it has the same update message and the refresh drawing at the end. Let's go to the compile and run. So now let's zoom in. And let's move it. So that's fine. Did anyone see something wrong from what I just did? So when we're selecting, we are not selecting the one that we thought we were selecting. And that is because we are finding the closest intersection. But intuitively, for a human, we expect the intersection to be at the center of the square. But it is actually at the lower left corner of the square. So when we thought we were clicking on that one, we're actually selecting the other one, where the lower left corner is closer than anything else. So we now want to move the actual intersection location to be the center of the square. And in this case, because fill rectangle only accepts the lower left corner, we want to move our lower left corner by width divided by 2 and height divided by 2. So we want to subtract that with half width and half height. And now what we will get will be just wanted to prove that it matches what I just said. We have the subtraction of half width and half height. And if we want to do subtraction on 2D points, you can just subtract the 2 point 2D, ETGL point 2D, and it will work. It will subtract the width and it will subtract the height, the X and the Y. Let me make and run. Now we are doing the correct selections. Yeah. Anything clear up to this point? Because now, next we are moving on to something else. Okay, next I'll show you how we would add buttons to our program. As an example, I will show you the Pinkify button, which will, when you press on it, we will draw the map in pink instead of a white background. So creating buttons, first, we register an initial setup callback function. So remember we had the 4 null pointers before. Initial setup is the first one, and mouse click is the second one. So we want to register an initial setup callback function, and we create a button in the initial setup. Then we want to register another callback function in the initial setup for this button. So it's called when the button is clicked, and we will call it toggle pink, which will toggle a Pinkify global variable, and your redraw function will check the Pinkify global variable to see whether we're drawing this map in pink or in white. Does that make sense? So this is just what I just said in code. In the application.run, we do the initial setup along with the act on mouse code, and the other two are not used. In the initial setup, it will take it in the application and a new window. Because we're not using the new window, we're just commenting that out. We want to create a Pinkify button in the 6th row using application.createButton. We give it a name. This name is printed on top of the button. 6 means the 6th row. Toggle pink. And toggle pink is the callback function we're registering when we click on the button. Then we write the toggle pink function. And this callback function here also has 2 parameters defined with it. The GTK widget is something related to TK that we're not using in this example. And we have the application. And in this function, we are toggling the Pinkify global variable. We are having the Pinkify global variable as a Boolean. So we're toggling it from false to true to false. Then we want it to show up immediately, so we force redraw. So in the initial setup, we are just adding in the things that we want to add on to the program. And in this case, we're adding one button, which is Pinkify. If you want to add more buttons, you can just create more buttons. Yeah, in here. And you need a separate function, callback function defined here that you can write yourself. Yeah, that's the function that's called whenever someone presses on the button. And in here for Pinkify, we're just toggling the global variable and we are false redrawing. Then in the redraw function, because we have this global variable, we're checking for that. And before everything else, we want to print out the pink background. By filling a large rectangle around the visible world. And the visible world can be obtained by g.getVisibleWorld. This will be a really useful one if you want to get your program to run faster later. And this color is just the RGB for the pink that we are going to use. Is this clear? And let's see it. So on that Pinkify, we have the draw main canvas Pinkify here, where we have the Pinkify check. And if we have Pinkify, then we drop a pink large rectangle first. And remember, we're drawing it first because it will overlap with other things if we draw it last. It will cover all the other things when we draw it last. So we want to draw it first and get the other things overlapping on it. And then we have the initial setup here. It's the same code. We create this single Pinkify button at the 6th row. And the rows start from 0. Toggle pink here, which toggles Pinkify and forces redraw. And I'll save it and go to the terminal. This is our map. Pinkify at the 6th row. And let's prove that it's the 6th row. 0, 1, 2, 3, 4, 5, 6. And this will toggle a pink background. If we move it, it's the same pink background. Okay. I think I forgot to show you the global variable. Defined here. Average lot is for conversion. Okay. Is that clear? And that's it for this week's tutorial. Any questions? Is anything unclear? Is anything you want me to go back to?